Okay, so today we will be start with the next chapter. That will be active filter. And now you can see what's going on here. Square wave, make it up a fundamental side wave and an infinite number of odd harmonic. So that will be telling you this is the square wave. Okay, basically square wave they make it up by the side wave at a different harmonic. Okay, now the first thing that you can see, you can get the fundamental. Okay, for the side wave. That I give you example. Fundamental is 1 kilohertz. And odd harmonic, that means third harmonic here. Okay. Then what the frequency for third harmonic?
3 kilohertz.
3K.
3K.
3 kilohertz. And if you get the next one will be fifth harmonic, 5 kilohertz, and keep going. And that's why they make it up for the square wave. Okay. So basically the square wave make it up by sine wave with the infinite harmonic. Now, if you're looking at the square wave display on the oscilloscope, okay, that will be displayed on the oscilloscope. And that's why you get a square wave -1 and to +1 volt, 1 millisecond for frequency, okay? However, when you display the same signal on the spectrum analyzer here, spectrum analyzer will be a frequency domain. Oscilloscope, that will be T. You see that time domain. On the spectrum analyzer, they will be displayed by different frequency. For example, the first one is 1 kilohertz here. What the amplitude of the signal, okay? But you cannot see any sine wave. And at the third harmonic, you can get what the value of the amplitude here, and they keep going, okay? That they telling you picture of 1 kilohertz square wave will be displayed on the spectrum analyzer. Spectrum analyzer, they vary with the frequency here, okay? That means for each frequency, what the amplitude of that signal.
And Mr. Pham,
Yeah,
just real quick, on that time right there where it says 0.9 volts and then it says 1.27 volts. Okay, so where is that related to?
which one? You're talking about what the, on the time frequency
On
domain.
the spectrum analyzer.
Okay, so what the odd
For
harmonic,
1K hertz at the top where the arrow is that it says 1.27 look like volts peak, and then above that it's just got 0.9 volts. So as it goes down the line, how is it generating those voltages?
I think that could be an average, like a DC.
You can mute the mic.
It turns out that square wave has if it has a fundamental of amplitude 1, the third harmonic is an amplitude of 1/3, the fifth harmonic is an amplitude of 1/5, and so on and so on.
Okay.
That's just what makes a square wave.
Okay, got it. And then but how? Okay, but the first one is just 0.9 then, right?
Yeah, it's like it's probably the RMS voltage or the average voltage. If you
Okay.
divide, yeah.
And then the last question is, what is the 1.27 and the millivolts and all that, the number on the below? Where does that come from?
This is just some arbitrary amplitude, right? Maybe it's for a 1 volt square wave. That's how the components break out by harmonics.
Yeah, I was just trying to figure out where those numbers came from and what they mean or whatever.
The thing that you see on the display on the oscilloscope, they get a 1 volt, right?
Correct.
Okay, so basically on that spectrum analyzer, they display 1.27 V peak. Okay, so if you get a V peak, you can try to say, you can calculate back to the VIMS or V average, see what they get.
Yeah, I get you. Thank you. Thank you. Thanks, Richard.
That's okay. Now, this is another display. Okay, 1 kilohertz square wave, 500 millivolt per division, 200 microsecond per division on the oscilloscope. Okay, and then also they can give it to you the signal display on the spectrum analyzer. 1 kilo fundamental. Okay, and they get a fundamental voltage in 900 millivolt. Okay, and for 8 different harmonics, they can tell you what is the value. But only thing we emphasize here, for the spectrum analyzer, they just display to you a signal at a certain frequency and telling you the amplitude of that signal. Okay. And now, what is the filter? Filter are circuits that can capable of passing signal with a certain selected frequency, while they will be rejected signal with other frequency. Okay. This property we call selectivity. Now, basically, filter just allow certain frequency to pass. Okay, and block the other. So that's why you can see the cable come into your house, go into the TV. The signal transmitted on the cable, they get two different types. One will be the picture. The other one will be the voice. Okay? So basically they must get the filter, okay, in order for the voice can go into the speaker. And the picture will be going to the display. Okay, so that's just telling you how the filter working. Active filter is transistor or op-amp combined with a passive RCRL or RCL circuit. The active device provides the voltage gain, and the passive circuit provides the frequency selectivity. So basically, what frequency you want to select it, that will be coming from passive. That means RCL device. Okay. The 4 basic category of active filter will be a low pass filter, high pass filter, band pass filter, and a band stop filter. Okay. first thing we go with the low pass filter. In general, low pass filter, they will pass any signal with the frequency lower. Okay? However, lower what? We go into the detail. Okay, now, this is stand for the gain. Okay? AV equal V out divided to V in. So at this point right here, do you know what they call for this one here?
Brick wall filter.
Midpoint,
Cutoff frequency.
mid-range.
Cutoff.
Range. This is what they call a mid-range. Okay, what happened at the mid-range? You know what happened?
The signal should lower to -3 dB.
No.
No,
Signal is allowed to pass at mid-range.
At mid-range, what the gain equal?
is the gain 1 there?
Exactly. Mid-range means the gain equal 1. That means the input and output will be the same, right?
Right.
So at the mid-range, no loss. If you're coming out 10 volts, you're coming out 10 volts, no loss. If you're coming out 10 volts, you're coming in 10 volts, you're coming out 5 volts, you get loss. Okay? Now, that's why they say 0 dB here. That means the gain equal 1. The thing is you take the 20 log of 0 to get a 1. Okay? And this is the ideal output response, mean output. That means at this point here, they don't want any more signal. So that's why the bandwidth, what's the bandwidth for the low pass filter, ideal op amp? This already telling you the bandwidth right here. They will be going from a 0 hertz to cutoff frequency. That is the bandwidth. Now, when you go into basically we deal with the practical output, okay? Then this is the mid-range right here. However, go to the point at this point right here. You going down, you get a cutoff frequency. And the cutoff frequency, the gain will be going down 3 dB. So if you get the input is 10 volt, okay, and the output will be going down 3 dB. So at the 3 dB, what the voltage?
7.07.
Yeah, 7.07.
7.0, 7.07 volts. That means minus 3 dB equivalent to 0.707, right? That means you take the 20 log of 0.707, you get minus 3 dB. So if you get a 10 volt, okay, and they down 70.7%, equivalent to 0.707, then you take 10 times 0.707. That's why you get a 7.07 volt, okay? Basically, dB, just telling you in general, you cannot using dB in order to find out what the voltage, okay? And now they say the slope in 20 dB per decade. Try to understand what they mean for 20 dB per decade. Decade means 10, okay? That means they telling you they going down, okay, with the speed of 20 dB per decade. FC, cutoff frequency, decade means 10 times. FC, that means 10 FC. Then they going down 20 dB. Now, if they going down 20 dB, can you telling me for the input 10 volt, what the output at the minus 20 dB? If you get the 10 volt, at the cutoff, they down 70.7% or minus 3 dB. In order to get the voltage, you have to take 10 times 0.707. You get 7.07 volt. And now I say, at the 10 times of FC, they down 20 dB per decade. Can you tell me at that 10 FC what the output should be? So
1/10.
basic minus 20 dB, you cannot find the way how to do in calculation. However, you have to know how can you get a minus 20 dB? So you take the 20 log 0.1 to see what you get. 20 log of 0.1.
It's minus 20.
Is it minus 20?
Minus 20.
Right?
Yes.
Minus 20 dB. Now, in order to do the calculation, then you have to take the 10 volt here times 0.1. So they will be 10 times 0.1, you get 1 volt.
Mr. Fan?
Yeah,
It's 20, it's at 10 FC, it's 20, it should be, somebody needs to mute their mic.
yeah.
Okay.
Yeah, go ahead.
Richard, you need to unmute your mic to speak.
Oh, sorry. Okay, so at 10 FC, the amplitude is 20 dB below the amplitude at FC, which is already minus 3. So isn't the amplitude at 10 FC relative to the 10 minus 23 dB?
20.
20 relative to what? To
No.
0.707 or to 10?
No. Now, normally they can going down 20 dB, 40 dB, 60 dB. Okay. So I can say going down minus 20 dB per decade, 40. If I give it to you a 1K cutoff, then decade for FC, that means add 10K. The question is, what the IM lead treat at the 10 kilohertz? Then they telling you, you going down 20. Then you have to find a number equivalent for minus 20. Exactly the same, like they say minus 3 dB. What the number equivalent to minus 3 dB? That means 0.707. And you take 10 times 0.707, you get 7.07 volt. And now they go into the minus 20. Then I said, you can using the 20 log. I try to find out what equivalent to minus 20. 20 log of 0.1, that's why I get minus 20. So you want to get the output, you have to take a 10 times 0.1.
Hey, Mr. Pham, I got you. What you said,
Yeah,
I got what you were saying. Somebody's mic need to be muted. Mute the mics again.
I mute it.
Okay.
Go ahead.
All right. So, could you, you was talking about minus 20 dB, and to get to minus 20 dB, you needed to know about 0.1. How did you know to use 0.1?
That's really hard to say. How do I know? Okay. But
I mean, is it an arbitrary number or?
no. That's a certain number. Have to be go with minus 20. I gave you another one. Now if they go say they down 40, minus 40 dB,
Okay, go ahead.
then what the value? Then you have to looking for minus 40 dB equivalent to what number?
0.01.
Exactly. You take 20 log of 0.01. You get minus 40 dB.
Okay.
So you take 10 times 0.01. And if they keep going another one more, then add it more 0.001 and so on. Okay?
Okay.
And I think what maybe Mr. Pham is assuming here, but we don't know, is that a single RC circuit, one resistor, one capacitor, has a roll off of 20 dB per decade. And that's called a single pole filter.
Right.
If you have multiple resistors and capacitors, then it can be a 2-pole filter, which is 40 dB per decade, or a 3-pole filter, which is 60 dB per decade.
Right. That means when we go next, you can see.
Okay.
Depend on the circuitry. They can telling you, is it a down 20 or 40 or 60 or 80?
But it has to have a resistor capacitor for one and two resistors, two capacitors for 2-pole, right?
Right. We come up now. Okay, in next page, they say 1-pole low pass filter. Okay, that's a 1-pole low pass filter. Only one resistor and one capacitor. Okay, low LPF only allow low frequency signal from 0 hertz to its cut off frequency FC point to pass while blocking those any higher frequency. Okay, cut off frequency or corner frequency or critical frequency is calculated by the formula Fc equal 1 over 2 pi Rc. Okay? In this formula, F have to be in hertz, R in ohm, and C is farad, pi equal 3.142. At the cutoff frequency, the gain is down 3 dB, or the output's going down to 77%, same as 0.707 of its maximum value. After the cutoff output decrease at a constant rate as the frequency increase. That is, when the frequency increase tenfold, 1 decade, the voltage gain is divided by 10. In other words, the gain decreased 20 dB each time the frequency is increased by 10. And now they're telling you 1 pole, 1R, 1C, roll off rate is minus 20 dB per decade, or 0.1. 2 pole, 2R, 2C, roll off rate minus 40 dB per decade, or 0.01. 3 pole will be 3R, 3C, and roll off will be minus 60 dB per decade, or 0.001. Now, we'll see on that one. They're using the dB. So basically 0 dB. That means no loss here. Okay, mid-range. And at the cutoff in here, okay, they will be going down to 0.707 or minus 3 dB. Then actual response of a single pole RC filter, okay, they going down with a speed of minus 20 dB per decade, okay. They're telling you increase the cutoff frequency 10 times, they will be going down 20 dB for 1 pole. For 2 poles, they will be the same, they will be going down 40 dB. Or 3 poles, they going down 60 dB. Normally, we only easy to recognize the single pole, but more pole, very, very hard to see, okay? However, we are the technician. When you're testing, they already telling you what is it, 3 pole, 4 pole, or 6 pole, whatever. And they asking you the output for its circuitry, okay? Very complicated, okay, for the filter. You understand the filter, we can build it in the lab for a few dollars. However, the one inside your cell phone, that will be cost a lot. That's why some cell phone get a different value. Pay more or less, okay? You pay more, you can get a very better for the voice and everything, okay? Also, remember, the bandwidth of the low-pass filter will be count from 0 hertz. That means the DC to cut off FC, okay? Now, this picture given you the different type, okay? First one is 2 pole here, okay? 1R, 1C. They're going down 20 dB. The next one will be 2 40 two pole. They going down at a speed 40 dB per decade. And the next one will be, okay, third, pole. So they going down quickly at a 60 dB per decade. So basically, this is the one you want. This is the one you want. Okay? So this is not good. The thing is too far away from the ideal. So 60 must be better than 40, and 40 must be better than 20 dB. Okay? And this is the ideal you want. Okay? So basically, the filter flow into the ideal. That's what really we wanted. Now,
Mr. Pham,
yeah,
I have a question. What is the other definition of the decade?
the definition of
Decade?
a decade, 10.
Okay.
That means, I'm giving you again. FC, you get a 1 kilohertz. Okay, so decade will be 10 times of 1 kilohertz.
All right, thank you.
Okay, they go by 10. The following show the output of the low pass filter with a different pole. We already see that. Okay, 10 times FC, same 10 times FC, same decade. 3 poles, you're going down 60 dB. 2 poles, you're going down 40. And 1 pole, you're going down 20. Okay? So now, you try to doing for me for this circuitry here. For the low pass filter, so you get R equal 1K, C equal 0.1 microfarad, V in equal 10 volt IMS. First thing they want to know what is the gain of this circuitry.
DC gain is unity gain.
But the gain equal what? Okay, can you tell me they're using what the op amp to build the filter? What's the name of
So
this op amp here?
it's a voltage follower, unity gain voltage
Follower.
follower.
Okay, they're using the voltage follower to build the filter. So I know for sure the gain must be 1, right? And now you have to do it for me to get the cutoff frequency. You know the cutoff frequency they already given to you right here. FC equal 1 over 2 pi RC. Go ahead and do a calculation for me.
1.6.
You say 1.6.
Yes, Mr. Fan, 1.6.
Okay, you say 1.6 kilohertz. Okay, so
Oh, so on that one there, that's you gotta flip the formula around and solve for R, correct?
what do you mean?
Never mind.
Number 2, I want to calculate the cutoff frequency. You're using the formula 1 over 2 pi RC. And you come up with one student give it to me 1.6 kilohertz. Make sure you're able to get it. Don't just copy the answer. the thing is sooner or later you still have to do that very basic calculation. And then what the VO at the cutoff?
Point 707.
0.707 times VN, which is 7.07 volts RMS.
It's a 7.07 VIMS. That means at the cutoff, output will be going down 3 dB, equivalent to 0.707. You take the 0.707 times 10 volt. That's why you get 7.07 volt. And the last calculation, they want to know Vout at the 10 times FC.
0.707.
Haha. How do we calculate at 10 FC? That means they're going down minus 20 dB.
Right, from the value at FC. So it's 1/10 of that,
10 volt,
0.707.
10 volt IMS, and now they're going down 20 dB. So they will be a 1 volt IMS, is it right?
I don't think that's right, Mr. Pham, because it's the frequency ratio from FC to 10 FC. So your starting voltage has to be 707, not 1. At 10 FC, you're 23 dB below 10 millivolts, 10 volts RMS. It has to be 0.707.
Okay, now, at that minus 3 dB, output them going down to 7.07. Okay? And the question next will be, when they increase the 10 times of the cutoff, then what the output supposed to be? Nothing to relate it into the 707. The thing is you going down 20 dB, or equivalent will be 0.1.
Okay, but there's a problem. Mr. Pham, I think there's a problem with your figure here. You're showing gain at FC is equal to 0 dB, but it's not. It's minus 3 dB.
What?
Your figure above the question shows the gain at FC is equal to 0 dB.
Hold on. The gain of the circuitry will be 1, correct? Is it the gain of this circuitry equal 1? Is it correct?
At below the cutoff frequency, the gain is
No,
1. Because
I'm talking about in basic first. I said this is the gain equal 1.
yeah, it's a voltage follower. So you can take that out of the circuit and just look at the passive elements.
Okay, so either I don't care on this circuitry here. If you get a 10 volt in, you get a 10 volt out. Is it correct?
Yes.
Yes.
Okay, now when they adding, make it a filter. So cutoff frequency equal 1.6 kilohertz. Now I want the output, okay, at the frequency 1 kilohertz. With output.
No, 16 kilohertz. Right?
What do you mean 16 kilohertz?
10 if FC is 1.6, then 10 FC is 16 kilohertz. So you do the calculation at 16 kilohertz for the decade.
Yeah, that's talking about decade. Right now, I'm not go to that point. I said, okay, if I get the frequency at 1 kilohertz, can you tell me what output?
$10.07.
Okay, now I can say cut off right here is 1.6 K. I asking you about signal at a 1 kilohertz, maybe here. So that will be right here. What the output?
707.
How come you come 707?
No, approximately 10 volts because the gain is 0.
That means the
dB.
gain 0. That means input output the same.
Oh, yeah.
So that means at that point, you will be get 10 volt IMS. In 10 volt, how will be 10 volt? That is mid range. Now at this point right here, they will be going down 3 dB. That's why you calculate you get 1.6 K cut off here. And the output, they will be going down 3 dB, means 7.07 volt IMS.
Hey, Mr. Pham, you put your dot at the, you said that's minus 3 dB, but you got 0 as minus 3 dB.
That is they using for ideal. Okay. If you want it, you have to go for the one really they going down. Let's see. Like this one. Okay. But that's what I say at the minus 3 dB. You don't care about this thing. They can be going little down here. Okay. Minus 3 dB. Then you calculate the cutoff, you get 1.6 K. Okay. Then you say output now will be 7.07 volt IMS. Is it right?
Right, go ahead.
Now they say VL at 10 times. 10 times up, FC will be 16K. Right?
Right,
So they going down 10 times FC. They going down with a slope 20 dB per decade. Okay? 20 dB per decade. And you understand that 20 dB means 0.1. And 0.1 will be time 10 volt IMS. Then they're supposed to be a 1 volt. Okay, anything, go ahead and bring it up. Okay, we can try to see.
I think if you do the calculation rather than just apply the 20 dB factor, you'll come up with a different answer. I'll do the calculation.
The thing is when you can get your assignment for filter, that will be verified for you, for my understanding. And another question. What we are at the 100 times FC. That means another 10. Okay, anywhere, when you get the assignment, you can get it from me. Okay, now you do this for me. Everything we already learned, except for the filter. On the filter, we need to calculate the cutoff frequency. What the name of the circuitry to build the filter? What the configuration? You know this circuitry here. They
It's
using
non-inverting.
non-inverted, correct. They using non-inverted,
So the gain is going to be 1 plus R2 over R1.
right, using non-inverted.
R2.
And again, ACL
9K divided by 1K.
plus by R2 over R1, right?
Mhm.
Okay, so you go ahead and do the calculation for me. Gain equal what?
10.
10. Okay, good. Cutoff frequency, same formula. 1 over 2 pi RC. Who get the answer for me?
Point 16.
0.1616. Okay. Will be 10K. Okay, 300 nano. Nano will be what power?
-9.
Make sure.
-9.
-9 or -9, whatever.
Okay,
E to the -9.
3 here, 9 here. You can left over 10 minus 6. Okay, so now I try to say 2 times
160.
Yeah, I got 159.15, but you're rounding it off.
How you are
Kilohertz.
looking at sustaining pledges, how your understanding.
2 times 2 pi times 10,000.
Okay,
160.
is it a 159 or 15.9?
159.15. Did anybody else get that?
Yeah, I got 160 with approximate.
Yeah,
159.
So 159 hertz, right?
yeah, they rounded it. It's over 159, but they're rounding it off. So 160 or 159, whatever.
159 hertz.
Okay,
That's what I come up with.
Thank you.
that's what I come up with.
Yeah. Okay, what is the VL maximum?
You get V out from, the gain is V out over V in, so you flip it around and you can get V out. Is that correct?
VL equal V
Oh,
in
okay.
times the gain,
Right.
5.
25.
2.5
Oh,
times 10,
25.
25 volt. And then now they want to
well,
get,
they, I know, they went virtual, but
they want to get the V at the cutoff frequency.
17.7.
17.5.
Will be 25 times 0.707, right?
Yes.
17.6.7.
Oopsie.
0.67 or 68 volt IMF. And now you can calculate the VL at 10 time of the cutoff. 25 times 0.1, 2.5, right?
Yes.
NFC is
That means you take 159 times 10. I think you get 15.9 kilohertz. Okay, you guys already learned how to using PSPI.
And Mr. Pham.
Yeah.
How did you get your 17.68?
You check maximum voltage 25 times 0.707.
Okay.
Back to number 2, I just had a question on the calculation there. It's 1 over 2 times 3. I can't understand the numbers.
1 over
Pi.
times 2 pi, 2 pi, pi will be 3, 1 for 2,
2 times 3 pi.
1 for 2. That's a pi.
Okay. 2 times 3 point. I don't know. I'm sorry. I'm looking out on my phone. I can't tell what it is.
2 times pi.
Okay.
2 times pi times 10 times 10 to the 3rd power.
Okay. Perfect. Thank you.
Okay, you already learned the PSPI simulation. That will be using for the frequency domain. Now, we already learned 2 different simulation programs. One will be MSIM7. The other one will be PSPI. Okay, MSIM7 basically close to what you really working on the test equipment. PSPI more theory, okay, than the other one. But they do the same job. Okay, go next. High pass filter. Now you can really understand it. High pass filter will be allow any frequency higher than cutoff to pass, and less than cutoff they will be attenuation. Okay, so this is a one pole high pass filter. And also they using the same follower unity gain amplifier to build. They just change the position of R and C. R up here, C down here, low part, and now C going up, and R will be going down. Okay, and you can see in the output for high pass filter. This is the cutoff. That means FC divided by 10. Okay, this is the FC right here, cutoff frequency. Go to the right, they will be bandwidth or pass band. Okay, into the left, they will be reduced. Okay, for this circuitry, they given UV in to VIMS are 910 ohm. C equals 0.1 microfarad. They want to know the gain of the circuitry. We already know, right? Gain equals 1. Cutoff frequency, you need to do calculation and tell me what the value. You understand the low pass and the high pass will be the same thing. Just opposite.
Why do we need the op amp if the gain's 1?
You can use using inverting, okay. You can using non-inverting. You can using follower. Doesn't matter. Only the difference will be the gain. At the beginning, we already telling you. Okay, active component. That means op amp will give you the gain. However, passive component RCL will give you a different frequency. So not why we using follower. You can using any inverting, non-inverting, or follower. Depend on the purpose of the design filter. Engineer, they can using either one.
Another advantage is that in this configuration, the op amp doesn't load the RC circuit, so it doesn't change the frequency response.
Circuitry op amp not change any frequency. Frequency changing based on I and C. The thing is cut off FC going 1/2 pi RC. So depend on what R, what C, you get a different cutoff frequency. Okay, who get the number 2 cutoff frequency? Let me know.
It's very big.
$17.49.
You get
Kilohertz.
17.
49.
But it is kilohertz, I think.
49 hertz.
Right.
Let's see, anyone else?
It's hertz, yeah. Because it's the resistor is only a little bit off from the 1K. It's lower than the 1K in the previous one, so the cutoff's higher. Right?
35K.
Oh, yeah.
And V out would be, V out at FC would be 1 times the 2 volts RMS VN.
You mean VL at FC, right?
Yeah, that's what I got. Unless somebody else got something different.
So what you get the answer? 2 times
1.414.
Yeah,
Mhm.
0.7.
Oh, maybe I did it wrong.
You get 1.4.
Okay, I messed it up.
Okay, so that one here, at 10
Yeah, I
will be
did.
0.2.
That's right. 0.707 times 2. Hit the wrong button.
The next one we're not doing now. I just given you going to that one quickly. Okay, the thing is we have to take the quiz. We already get the high part. We already get the low part. They can be 2 pole or 3 pole. Doesn't matter. 1 pole they down 20 dB. 2 pole they down 40 dB. 3 pole they will be down 60 dB. And now the band path. First thing, if you're looking into the circuitry, we know this is the one they're using op amp to build. Okay? And they adding capacitor resistor to make the band pass filter. So basically, the band pass filter for the first one, they get this one here. That means they combine high pass filter to the low pass filter. That's why they make a band pass filter. Okay? The thing is, you can see this is the high pass filter go this way. That high pass filter. And a low pass filter, they go the other way. So this is the one will be band pass filter. So band pass filter, they combine between the high pass circuitry and the low pass circuitry to make the band pass. And the band pass, they get a true cutoff frequency. Okay? This is go to the minus 3 dB. And you get a low cutoff and you get a higher cutoff. And the bandwidth, they will be going from low to high. That will be the bandwidth. Any signal higher than F high or lower than F low will be reject. Okay? Only frequency between the cutoff low and the cutoff high allowed to pass through it. That is basically band pass filter. This gives you more picture. Okay? So pass frequency higher than F1 and less than F high. There's F low, F high here. Okay? From F low to F high, you get that one the bandwidth. Bandwidth equal F high minus F low. If you want to calculate the center frequency here, they will be equal square root of F1 times F2. Then you get the quality Q. Quality, that means how good the filter do it. Equal F center divided to the bandwidth. Quality Q control the roll-off rate and the bandwidth of the filter. Okay? Okay, so basically you get the time. You try to go through it. Okay? Try to read not much, nothing. Okay? Okay, we will continue after we return. The thing is, after the filter, then I will be go to the JFET transistor. On off the major for the electronic, we try to finish it first, and we get more review to keep you guys understanding and memorize what we need.
Hey, Mr. Pham,
Another
could you,
thing like comparator, okay, integrator, differentiator circuitry, that it will also go through it, but not the major. Okay, so any question? Otherwise, we have to take the test now.
yeah, real quick, Mr. Pham, can you go back to that slide where the last problem? One more. One more. Right there, right there, right there, right there, right there. The very last question, number 4. Just tell me how you got that again, because I keep getting it wrong. Number 4.
That means they get a minus 20 dB.
Okay.
Minus 20 dB means 0.1. You take a 2 volt times 0.1.
Okay, got it.
Okay, make sure you download your report for the quiz. Okay, I run it now. Uh-oh. Sorry.
Yeah, thank you.
Ha 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 ha. How come?
That's okay right there, Mr. Fan. We can keep going.
Uh-huh. Just a minute, okay.
Sam and Mr. Pham, I think the units on the answer sheet of question 16 are wrong.
Yeah, don't worry. Yeah, just think about that volt. Oh, they gain. Let's see. Yeah, they want the gain on that.
It should be no dimensionless.
Yes. which is NA, not applicable.
It means they don't have a value.
Or either that or don't do it.
It's dimensionless. It's just a ratio.
Okay, so everyone will get a very good spring break.
I think we still have tomorrow, and yeah, we still have tomorrow. Today is Wednesday. Thursday was Mr. Tai tomorrow. Okay, so look like everyone's good.
See you on Sunday.
You wish. If I can make it to Sunday.
Bye. Have a good week. Get out of there.
It's not a guarantee. It's not a guarantee.
Bye-bye, everybody.
Bye-bye.
Bye-bye.
Hi, thank you.
You're welcome.
See you next week. Oh, no, next month.
Good night.
Good night.
Next year.